Okay, when 4-ketopentanoic acid is analyzed by combustion, a 0.3 gram sample produces 0.579 grams of carbon dioxide and 0.142 grams of water. The acid contains only carbon, hydrogen, and oxygen. What is the empirical formula of the acid? Let's walk through these steps together. Calculate the mass of the carbon present in the combusted sample. So the first thing that we're going to want to do is convert the given mass of carbon dioxide, which in this case that is the 0.579 grams, to moles of carbon dioxide produced. Since there is one carbon atom in one molecule of carbon dioxide, this is the number of moles of carbon present in the original compound. Convert the moles of carbon atoms to mass of just carbon. So where are we going to start here? Well, there's a couple of key pieces of information. The first is the total mass that we're dealing with. So the total mass here is 0.3000 grams. And notice how it's going out to basically 4 decimal places. That tells us that our answers, as we work through this, we want to take it out a couple of decimal places. They also tell us the mass of carbon dioxide is 0.579 grams, and the mass of the water, which we're going to use later, is 0.142 grams. All right, so what we're doing here is we're converting the given mass of carbon dioxide to mass of carbon. That's what we're doing. So the first thing that we're going to do is write our given. 0.579 grams of carbon dioxide. Okay, after we do this, we're going to convert to moles. So now multiplication sign in a line. I know that the gram formula mass of carbon dioxide is 44 grams of CO2, and we're converting that into 1 mole of CO2. Converting it into 1 mole of CO2. Now I'm in moles of CO2. Now, this next step is key. I want to get out of moles of CO2, and I want to get into moles of just carbon. So we know that 1 mole of CO2 is equal to 1 mole of just carbon. Because in this original sample of carbon, we just have 1 mole of carbon because there's no subscript down here. It's an assumed 1. So now I'm in moles of carbon, and I want to go into grams of carbon. So because that's the final thing that I want. And we know that 1 mole of carbon is equal to 12 grams of carbon, the atomic mass of carbon. Now, do I know I have this set up correctly? I should be able to cancel everything. So grams of carbon dioxide cancels grams of carbon dioxide. Moles of carbon dioxide cancels moles of carbon dioxide. Moles of carbon cancel moles of carbon. I'm left over with grams, which is what I want. So my final answer here for grams of just carbon out of this original sample that I was starting with is going to be 0.1579. I said 9. Oops. 9 grams of carbon. All right, so we've done the first step. We've calculated the mass of carbon present in the combusted sample. Let's go on to the next step. Calculate the mass of now the hydrogen present in the combusted sample. Convert the given mass of water to moles of water produced. That's going to be step 1. Since there are 2 hydrogen atoms in one molecule of water, multiply this number by 2 and calculate the number of moles of hydrogen atoms present in the original compound. This is a key situation right here. Very, very key. Convert the moles of hydrogen atoms into mass of hydrogen. So let's go back and see our original mass of water. And our original mass of water is 0.142 grams of water. Now I'm going to convert that into moles. So my first step will always be taking my mass of water and converting it into moles of water. I know that there's 18 grams of water in 1 mole of water. 1 mole of water. Now this next thing, I'm in moles of water, but I want to get into moles of hydrogen. So I know that in 1 mole of water, there is 2 moles of hydrogen atoms because of this subscripted 2 right there. That's really important. And every time you do this type of problem when you're dealing with hydrogen, you're going to have this particular step here. So 1 mole of water is always equal to 2 moles of hydrogen. The last step is to get my moles of hydrogen into grams of hydrogen. So 1 mole of hydrogen is equal to 1 gram of hydrogen. And again, I go through and I make sure that I've set this up correctly. So grams of water cancels grams of water, moles of water cancels moles of water, moles of hydrogen cancels moles of hydrogen. I'm in grams of hydrogen, which I want at the end. And again, when I write my answer, which is going to be 0.01577 grams of hydrogen, I'm going out a bunch of decimal places. That's really, really important. I don't want to round at all at this point. Now let's go on to the next step. If there is another element present, typically oxygen, in the combusted substance, then calculate its mass by subtracting the mass of the carbon and the hydrogen from the total mass of the combusted sample given. So what was my total mass? My total mass was 0.3000 grams of substance. I'm going to subtract my mass of carbon, so 0.1579 grams of carbon. I'm going to subtract my hydrogen that I just found on the previous slide, so 0.01577 grams of hydrogen. And when I subtract these two amounts that I found from my original sample, I find that my mass of oxygen is 0.12633 grams of oxygen. Excellent. So now I have my 3 masses. My mass of carbon, my mass of hydrogen, and now my mass of oxygen. So I can go on to my next step, which is calculating the empirical formula. Okay, so step number 4 is take the calculated mass of the carbon, hydrogen, and oxygen that we found in the previous step and convert them all into moles by dividing by the appropriate atomic mass. Finally, we're going to find the smallest number of moles calculated and divide all of the numbers of moles by that number. So this is basically the same thing that we did before to figure out empirical formula. Now remember, avoid rounding up or down too much at this stage and be lenient with significant figures. So what are we really doing here? Well, we know from the previous steps, from step 2 and step 3, that we had 0.1579 grams of carbon and 0.01577 grams of hydrogen, and we had 0.12633 grams of oxygen, and we found that, remember again, from step 3. Now what I'm going to do with all of these is convert them into moles. So 1 mole of carbon is equal to 12 grams of carbon, and 1 mole of hydrogen is equal to 1 gram of hydrogen. So we're going to find that. And finally, 1 mole of oxygen is equal to 16 grams of oxygen. And again, I know I have set this up correctly because grams of carbon cancels grams of carbon, grams of hydrogen cancels grams of hydrogen, grams of oxygen cancels grams of oxygen, and I'm going to get the right unit of moles of carbon at the end. So when I work this out for moles of carbon, I'm going to get 0.01315 moles of carbon, and I'm going to get 0.01577 moles of hydrogen, and I'm going to get 0.007895 moles of oxygen. Now we're on to step 5, which is right here. Find the smallest number of moles calculated, try to figure out which one of these is the smallest one, and divide all of the numbers of moles by that number. So when I look at these, the number that is the smallest is the moles of oxygen. So each one of these, including the oxygen, is going to be divided by 0.007895. This one is going to be 0.007895. And finally, 0.007895. Now when I divide all these out, I find out that I get 1.66 for that, 1.9987 for that one, and of course 1 down here. Now here's the issue that we have. The 1's fine. This is close enough to 2 that we could round this to 2. That's really not an issue. But this 0.166 is sort of an issue. It's not really close enough to 2 to round it up to 2. So what we need to do here is we need to multiply all of these by 3. Because I know that for 0.66 or for 0.33, if I multiply it by 3, I'm going to get near a whole number. And when I do that, this turns into 5, this turns into 6, and this turns into 3. And remember, these represent subscripts of each of these elements that I started with. So my final answer here for my empirical formula is going to be C5H6O3. And to be honest, the majority of the time, these are going to be close to whole numbers, so you won't have to do this step. But I thought I'd show that to you anyways, just so you had an idea of what to do with it. And we'll look at more examples of that. So the results from the previous step should be in a convenient ratio and give the empirical formula. Note, it may that the ratio includes a fraction such as 0.5, 0.25, or 0.33, or in the case that we just saw, 0.666. If so, then multiply all numbers by either 2 or 4 or 3 as appropriate to remove the fraction. If necessary, use the molar mass to turn the empirical formula into a molecular formula.